Hello, my name is Youngmin Kim. Today I'm gonna talking about the paper named Learning Transferable Architectures for Scalable Image Recognition on CPPR 2018. Neural architecture search is a method by which network algorithms find themselves optimized structures. In 2017, a method of finding hyperparameter for each layer using RNNs and reinforcement learning was proposed, named NAS. NAS renews layers of our network at once. This makes the searching space of NAS big. As such, optimizing the NAS is time-consuming and costly. It spent 28 days using 800 GPUs. Compared to NAS, NASNet significantly reduced the cost of finding the optimal model. How was that possible? That is because the search space was decreased. Not search the entire network, but the small unit, and find the optimal combination of them. In other words, they find the network in a bottom-up method. First, let me explain the smallest unit, named block. As shown in the figure above, the value of 5 RNN controllers determines one block. 2 hidden state inputs, 2 operations, and 1 combined operation are determined. First 2 RNN layers determine the operations input. Second, following 2 RNN layers determine the operation type, and there are a total of 13 types of operations. Final RNN layer determines the combination method between the operations. If the B block sequentially generated like this, the convolution cell will be determined. There are 2 types of cells, normal cell and reduction cell. A normal cell is a cell that does not reduce the spatial size of the feature map, while a reduction cell reduces the spatial size. Both the reduction cell and normal cell are generated the same structure, and the only difference is the stride of the operations in the block. When configuring a normal cell, the strides of the operations are fixed at 1, while the stride value of the reduction cell is either 1 or 2. A network is defined as repeating the previously defined normal cell and reduction cell. What's interesting is that all the convolution found in the optimal model are depth-wise separable convolution. Once again, you can see that depth-wise separable convolution is the efficient way when finding trade-off between computational cost and performance of the network. Next, I will talk about the result of the experiment. First, comparison with state-of-the-art model on CyPA10. When cutout was applied to shake regularization, with the 2.56% error rate was the lowest. But NASNet shows that a lower error rate of 2.40% could be achieved with almost this small number of parameters, in case of NASNet-A with cutout. Second comparison with state-of-the-art model on ImageNet. They didn't find the optimal network with the ImageNet dataset because of the large scale of the dataset. They just referred to structure that worked well in CyPA10. However, they achieved the highest performance among existing networks with a significantly smaller number of parameters compared to former state-of-the-art model named SENet. In this paper, they found that optimizing small units can reduce search space when doing auto-architecture search. We can see that the method of optimizing from small units is good in terms of generalization. This has been demonstrated through experiments with changing dataset. Once again, we can see that the superiority of the depth-wise separable convolution to find the trade-off between performance and efficiency.